The first set will be problems related to continuous time Fourier transform. Continuous time Fourier transform, CT, FT. Okay. Find Fourier transform of A xt equal to e to the power minus 2t u of t minus 3. Okay. How to solve this problem? See, we know the formula of Fourier transform, which says that x of j omega is equal to minus infinity to infinity x of t e to the power minus j omega t dt. So in this I can write 3 to infinity, because u of t minus 3 starts from t equal to 3. E to the power minus 2t e to the power minus j omega t dt. This is equal to 3 to infinity e to the power minus 2 plus j omega t dt. Okay. On solving this, e to the power minus 2 plus j omega upon minus of 2 plus j omega 3 to infinity. So when I put infinity, this becomes 0. When I put 3, 0 minus e to the power minus 3 2 plus j omega upon minus of 2 plus j omega. This is equal to e to the power minus 3 2 plus j omega upon 2 plus j omega. Okay. This way it can be solved. Okay, it was not visible when I was solving, so you can see the solution once again. 3 to infinity minus of 2 plus j omega t. We have to solve this integral. On solving this integral, we will get this 3. When we put infinity in this, it becomes 0, and putting 3, it is solving finally and get the result this. Okay. Next one will be xt equal to e to the power minus 4 mod t. For this, we have to find the Fourier transform. Now, the formula is same again. X of j omega minus infinity to infinity. The formula minus infinity to infinity to the power minus 4 mod t or e to the power minus j omega t dt. So with this I can write minus infinity to 0 e to the power 4t e to the power minus j omega t plus 0 to infinity e to the power minus 4t dot e to the power minus j omega t dt. Okay, this also dt. Now this I can write it as 1 upon 4 minus j omega plus 1 upon 4 plus j omega. That will become 8 upon 16 plus omega square x of j omega. If we see this x of j omega, it has only magnitude response. Phase response is 0. Okay. Next problem. Xt is equal to signum function of t. Find the Fourier transform of this. First of all, signum function is this. Okay. So I can write signum t to 1 for t greater than equal to 0, minus 1 for t lesser than 0. Okay, this is signum function. Now using again the formula x of j omega minus infinity to infinity signum function t e to the power minus j omega t. I can write it as like this: minus infinity to 0 minus 1 e to the power minus j omega t dt plus 0 to infinity 1 dot e to the power minus j omega t dt, which is equal to e to the power minus j omega t upon j omega minus infinity to 0 plus e to the power minus j omega t upon minus j omega 0 to infinity. This gives me 2 by j omega. Okay, the Laplace transform, the Fourier transform for signum function is 2 by j omega. Now, before taking third problem, we will just understand what is duality property. Duality property says that if xt has got a Fourier transform x of j omega, then then 2 pi x of minus omega is equal to x of Yusuf kt. Okay, this property will help in solving the many problems. We'll just see the examples. Find Fourier transform of xt equal to 1 upon a square plus t square. Okay, we know e to the power minus a mod t. Just now we have solved one problem which gives me Fourier transform of 2a upon a square plus omega square. Okay, thus 2a upon a square plus t square will have a Fourier transform of 2 pi e to the power minus a mod of minus omega, which is equal to 2 pi e to the power minus A mod omega. Okay. Okay. Thus, Fourier transform of 1 upon A square plus T square will be 2 pi e to the power minus A omega upon 2A, which is equal to pi upon A e to the power minus A mod omega. Okay, this way this problem is solved. Next, another problem, problem number 4. Find Fourier transform of x equal to unit step function. See, important thing is unit step function does not satisfy Dirichlet condition of absolute integrability. Okay, thus, but it can possess Fourier transform. See how. Ut can be written in terms of signum function as half signum t. Okay. So once if ut can be written like this, I know for 1 by 2 Fourier transform is pi of delta omega. Okay. Signum t has got Fourier transform 2 by q omega. This implies that 1 by 2 signum function will have a Fourier transform 1 by q omega. Thus, Fourier transform of ut using linearity property will be pi of delta omega plus 1 by q omega. Okay. In this way, Fourier transform of unit step function is found. Finding the time domain signal if Fourier transform is given, that is finding the inverse Fourier transform. First one, if x of q omega e to the power minus 2 mod omega, then find xt. Okay. Here again we can make use of duality theorem. Okay. Or we can also make use of the formula of finding the xt. Xt 1 by two pi minus infinity to infinity x of j omega e to the power j omega t. Now we can substitute x of j omega as 1 by 2 pi minus infinity to infinity e to the power minus 2 mod omega e to the power j omega t d omega. Okay. So again I can write it as like this, minus infinity to 0 e to the power 2 omega or e to the power j omega t d omega plus 1 by 2 pi 0 to infinity e to the power minus 2 omega dot e to the power j omega t d omega. On solving this integral, 1 by 2 pi e to the power 2 plus jt omega upon 2 plus jt minus infinity to 0 plus 1 by 2 pi e to the power minus of 2 plus jt omega upon minus of 2 plus jt. Okay, this limited from 0 to infinity. On solving this, it will become 2 by pi 4 plus t square. This is my xt. Okay, so these steps were hidden when we are writing. So we can find, we have written the two, we have solved the two integral. This integral is corresponding to this, and this one. On solving this integral and putting the limit from minus infinity to 0 and 0 to infinity, we will get finally 2 upon pi 4 plus t square. Okay, you can also verify it. Now using the principle of duality, I can write it as like this. X of omega will have 2 pi x of minus jt. Okay, so use this, we'll get the same result here. Okay, another problem. X of j omega is given as 6 j omega plus 16 upon j omega square plus 5 of j omega plus 6. Find the inverse Fourier transform or find xt out of this. We can make use of partial fraction here, okay, because after partial fraction, after doing partial fraction, we will get the term like x of j omega is equal to a upon 3 plus j omega plus b upon 2 plus j omega. Okay, finding a and b, I will get a equal to 2, b equal to 4. Thus x of j omega is equal to 2 upon 3 plus j omega plus 4 upon 2 plus j omega. Getting the inverse Fourier transform xt from this is 2 e to the power minus 3t ut plus 4 e to the power minus 2t ut. This is nothing but the Fourier direct evaluation of xt from x of j omega. We have to remember that e to the power minus at ut will have a Fourier transform as 1 upon a plus j omega. Okay. Next, find inverse Fourier transform of this. X of j omega is given as j omega plus 3 upon j omega plus 1 whole square. Okay, so solution. I can write it as like this: j omega plus 1 plus 2 upon j omega plus 1 whole square. This is equal to 1 upon j omega plus 1 plus 2 upon j omega plus 1 whole square. Okay, so this becomes xt will be e to the power minus t ut plus 2t e to the power minus t ut. Okay, we have used the property here. T xt will give me minus j d by d omega x of j omega. Differentiation frequency domain gives me with multiplication of time t in sequence time domain. Another problem, slightly different problem. xt has got Fourier transform x of j omega. Okay, xt is given by 1 and 0. It is 1 for mod t lesser than 1 and the 0 elsewhere. Okay, x of j omega corresponding to this xt is equal to 2 sine omega by omega. Find Fourier transform of this triangular wave. This from minus 2 to 2, amplitude is 2. Okay. How to find this? See, convolution of two rectangular pulses will give me a triangular wave. Okay, that means we are doing convolution in time domain. Now the convolution in time domain goes to multiplication in frequency domain. Now xt convolve with xt will have Fourier transform x of j omega multiplied with x of j omega. Thus Fourier transform of rectangular, sorry, this is not rectangular, triangular signal will be 2 sine omega by omega multiplied by 2 sine omega by omega, which is equal to 4 sine square omega by omega square. Okay, this way this problem is solved. So sometimes we have to be very careful while finding the Fourier transform of some things, because the Fourier transform can also be found by using the various properties. So the one use of that property we have seen here. Next problem. Find the frequency response of this system whose differential equation is given below. D yt by dt plus 2 yt is equal to x. Now I can write this differential equation in terms of Fourier transform as j omega y of j omega plus 2 y of j omega is equal to x of j omega. This implies that y of j omega upon x of j omega is equal to 1 upon 2 plus j omega. Okay, this term is equal to h of j omega is equal to 1 upon 2 plus j omega. Now we have to find the inverse Fourier transform of this, which is ht equal to e to the power minus 2t ut. Okay, this is the sequence. This is the frequency response, and this is the impulse response of that. Okay. We have seen some time back we have covered the topic of the frequency response of the system. So actually I should not be saying that only the complex exponential or a sinusoidal signal is applied. Frequency response can even be found for the exponential signal also, a normal exponential signal not containing any frequency component. Okay, for that we should say that the sinusoidal response or the system. Okay, because this also contains a frequency response 1 upon 2 plus j omega. Why frequency response? We will change here. We will see the variation of h of j omega. We will see the behavior of h of j omega with respect to frequency. Okay, so same thing when this is in frequency domain. That's why it's called a frequency response of that. Okay, so these were the few problems which we have covered in this frequency for problems related with continuous time Fourier transform. We will see problems for other continuous time Fourier series, discrete time Fourier transform, discrete time Fourier series, and after that we will cover the topic discrete Fourier transform. Okay, this topic is newly introduced in